Let us revise about the chemical kinetics. And as you know, this chemical kinetics, it deals with the rate of chemical reaction, means the speed of chemical reaction, rate of chemical reaction, and the factors affecting the rate of chemical reaction, and the factors affecting the rate of chemical reaction. And this rate can be, the rate of chemical reaction can be the average rate of reaction, which is the total change in concentration, upon the total time taken. Or it can be the instantaneous rate. Instantaneous rate means the rate at a given instant of time. Rate at a given instant of time. And this instantaneous rate is defined only for a infinitesimally small interval of time. For example, if this is the reaction given, A moles of A plus B moles of B gives M moles of M plus N moles of N, then the rate can be defined as the average rate, and average rate is equal to the change in concentration of A upon time, the total time taken, divided by stoichiometric coefficient. And this minus sign means it is disappearing with time, means the concentration of A decreases with time. That's why the minus sign is there, and is equal to minus 1 by B delta B upon delta T. This square bracket represents the concentration in moles per liter, and plus means the concentration of M increases with the time. It means this substance is on the right hand side of the arrow as a product. So again 1 by M delta M upon delta T, and is equal to plus 1 by N delta N upon delta T. And the rate can be expressed either as a disappearance of A, disappearance of B, or formation of M, or formation of N. Now when we write the instantaneous rate, it is for a very small interval of time when the delta T approaches 0. So this can be defined in the same way as the average rate, but only thing is we replace the delta by D. So minus 1 by A, it's a dA by dt. This is the instantaneous rate of disappearance of A. This is the instantaneous rate of disappearance of B. And similarly, this is the instantaneous rate of formation of M. And this is the instantaneous rate of formation of N. If we know any one out of these four, we can calculate the remaining three. Now suppose you are given this reaction N2 gas plus the 3H2 gas gives twice of ammonia gas. Now in this case, we can relate the rate of disappearance of hydrogen with the formation of ammonia by this equation. That rate is equal to minus 1 by 3 instantaneous rate of disappearance of hydrogen is equal to plus 1 by 2. This is the rate of formation of ammonia. Next point is that rate depends on the concentration of the reactants. Now, for example, if this is a reaction given, A moles of A plus B moles of B give products, then the rate can be expressed as, this rate can be expressed as a disappearance of A, disappearance of B, or the formation of product. But the rate is equal to K into A raised to the power X and B raised to power Y. This rate can be any rate. It can be disappearance of A, disappearance of B, or formation of any one of the product. Now, in this equation, this K stands for the rate constant, velocity constant, and X and Y are experimentally determined numbers, experimentally are determined numbers may or may not be equal to, not be equals to the stoichiometric coefficient, may or may not be equals to the stoichiometric coefficient. Now, this is called the rate law. This is called the rate expression. So, rate expression relates the rate with the concentration of the reactants and the rate constant. Now, in this equation, this rate constant is defined as the rate of a chemical reaction. It's the rate of a chemical reaction when the concentration of each reactant in the rate expression is equal to 1 mole per liter. That's the definition of a rate constant. Now, in this rate expression, this X stands for the order of a reaction with respect to A, and Y stands for the order of reaction with respect to B, and the overall order of the reaction is X plus Y. Overall order of the reaction is X plus Y, and this order of reaction is defined as the sum of the exponents is defined as the sum of the exponents to which each concentration term in the experimental rate expression. And this order is an experimental quantity, and order can be 0, it can be integral 1, 2, 3, or it can be in fraction also. And if the order is equal to 0, it means the rate and the rate constant have the same units, concentration per time. If order is equal to 1, then the rate constant will have a units of time inverse. And in general, for the nth order reaction, the rate constant will have a units of concentration raised to power 1 minus n, where n is the overall order time inverse. So if we know the order of a reaction, we can derive the units for K, and if we know the units of K, we can calculate the overall order of the reaction. For example, this. Now this is a reaction given, A plus 2B gives C has a rate constant value equals to 1.36 into 10 raised to power minus 3 liter square mole minus 2 and the second inverse. Now question is, what is the overall order of the reaction? What is the overall order of the reaction? Now in this case, look at the units. Now K has the units of mole liter inverse raised to power minus 2 second inverse, and we'll compare it to the general expression which is mole per liter raised to power 1 minus n and second inverse. So this gets cancelled. Now base is same, you compare the exponents. So we write minus 2 is equal to 1 minus n, or we write n equals to 3. So the overall order of the reaction is 3, but we don't know what is the order with respect to A, what is the order with respect to B, we don't know. We only know that the overall order of the reaction is 3, it's the third order reaction. And the order of the reaction can be calculated. Order of the reaction can be calculated from the initial concentration of the reactants. From the initial concentration of the reactants. This is called initial rate method. Now, for example, the rate of reaction becomes 27 times when we triple the concentration of the reactant R. Question is, what is the order of the reaction? What is the order of the reaction? So we assume that our rate equation is this: R is equal to K into R raised to power X. Now it states that rate becomes 27 times. So we write 27 R when we triple the concentration of R. Now we divide these two equations, and dividing these two equations gives 27 equals to 3 raised to power X equals to 3 raised to power 3. So X is equal to 3. So it's a third order reaction. Now we take one more question. Now this is a reaction given. A plus B gives C. And the question states that the rate becomes a double when we double the concentration of A, and becomes 8 times when we double the concentrations of both A and B. Now what is the order of the reaction and the rate law? What is the order of the reaction and what is the rate law or rate expression? Now we assume the rate law to be this: R equals to K into A raised to power X and B raised to power Y. This is our first equation. Now the first line of the question states that the rate becomes double. So we write 2R when we double the concentration of A. So B raised to power Y only. And then it states that the rate becomes 8 times when we double the concentration of both A and B. Now our aim is to find first X and Y. So we divide equation 2 by equation 1 gives 2 raised to power 1 equals to 2 raised to power X, so X is equal to 1. So order with respect to A is 1. Then we divide equation 3 by equation 2. It gives 4 equals to 2 raised to power Y, or Y equals to 2. So the overall order of the reaction is 3. Overall order is equal to 1 plus 2 equals to 3, and the rate law is, now put the value of x and y in the equation number 1. So rate law is R equals to K into A raised to power 1 and B raised to power 2. This is our rate law. Now in this expression, if one of the reactant is in excess, now suppose we assume, if we assume that B is in excess, present as a solvent, it means its concentration is not changing with time. And the concentration is not changing with time. As a result, B should not appear in the rate equation with time. Then the rate law is reduced to this, R equals to K into A. So the reaction which appears to be higher order reaction, the reactions which appears to be a higher order reaction, but are actually first order, as one of the reactant is in excess, are called pseudo first order reaction. Very, very important term, pseudo first order reactions. Examples are first hydrolysis of cane sugar or hydrolysis of an ester, and the second is the inversion of cane sugar. Inversion of cane sugar. So these are two examples of pseudo first order reactions. So this is all about the types of rates, average rate and the instantaneous rate, and the order of a reaction.